Applications of Gauss theorem. Gauss theorem is used to find electric field intensity due to uniformly charged distributed bodies. From those bodies, at certain point, what is the electric field intensity value? That is determined by applying Gauss law. By applying Gauss law, we determine the electric field intensity due to uniform charge distributed bodies for some symmetric charge configuration, nothing but uniform charge distributed bodies. However, it is possible to obtain the electric field in a simple way using the Gauss's law. For that, here we are going to find electric field intensity due to an infinitely long straight uniformly charged wire. This is the first application of Gauss law. Now, to calculate electric field intensity, now we are considering an infinitely long thin straight wire with uniform linear charge density lambda. Means throughout the length of the wire, some charge is distributed uniformly. That wire having linear charge density lambda. What is lambda? Lambda is charge per unit length. This is that wire. Now, on that wire, consider 3 points. What are that points? P, P dash, P double dash. These 3 points are situated at equal distance r from the conducting wire, charged wire. Hence, at all these points, the intensity of electric field is same. Now, the wire is obviously an axis of symmetry. The points P, P dash, P double dash obtained are completely equivalent with respect to this charge wire. With respect to this wire, P, P dash, P double dash all are at same distance. Why? Because this is a circular path. The wire is situated at the center of the circle. And P, P dash, P double dash are the points which are situated on the axis, which are located on circumference of the circle. Hence, all these 3 points having same electric field intensity. This implies that the electric field must have the same magnitude at all these points. Now, let us consider the direction of the electric field. According to diagram, the wire is positively charged and its length is infinity. Positively charged means lambda, linear charge density, is charge per unit length. That value is positive. That value is positive means lambda greater than 0. That means if the wire is charged positively at a given point, electric field is directed radially outward. If the wire is negatively charged, electric field intensity at a given point directed towards the wire, radially inward. So, lambda greater than 0, the direction of the electric field at the respective point is radially outward along this direction. If lambda is negative means which is less than 0. Meaning of this is the wire is negatively charged. Hence, electric field at a point is towards the negatively charged wire. So that we call radially inward. Now, consider a pair of line elements. What are the two elements? P1, P2. Observe these two elements as shown. Now, the electric field at everywhere radial in the plane and cutting the wire normally. Observe here. The wire is like this. Electric field is directed along this direction if the wire is positive. If the wire is negative, electric field directed inward. Whatever it may be, it cutting the wire normally, whether it is inward or outward. And its magnitude depends upon the radial distance of the point from the wire. Means on this R, this value depends. Now, to calculate the electric field intensity, here we are going to imagine a cylindrical Gaussian surface. Observe here. This is the wire. Around the wire, we are assuming a Gaussian cylinder. The name of the Gaussian cylinder is ABCD. Now, since the field is everywhere radial, flux through the two flat surface of a cylindrical Gaussian surface is 0. Let me explain this point. Here, for this AB surface, this is the AB surface. For this AB surface, the area vector directed like this. This arrow mark indicates area vector direction for AB surface. For this AB surface, electric field is directed like this. So this is E bar direction. How electric field and area vector are directed? These two are mutually perpendicular to each other. Hence, angle between electric field and area vector is 90 degrees. Now, flux through AB surface is equal to closed integral E bar dot ds bar. ds is area of this flat surface, which is equal to integral E ds. What is angle between area vector and electric field? 90 degrees. Cos 90. Cos 90 is 0. That means flux through AB surface is also equal to 0. Similarly, for CD surface, this is the CD surface area. The area vector for CD surface directed downward. Let us consider that area vector is A bar. And at this point, due to this positive charge, electric field is directed radially outward. May along this direction or along this direction. This is E bar. Again for CD surface also, A bar, E bar, both are perpendicular to each other. Makes an angle 90 degrees. Hence, flux through CD surface is also equal to 0. Means for two flat surfaces AB and CD, the flux becomes 0. Hence, the remaining surface is ABCD cylindrical surface. At the cylindrical part of the surface, E is normal to the surface at every point and It is parallel to any area vector on the curved surface. So, flux is not zero. For that, let us consider a small elemental area ds bar. This ds bar is directed along this direction. And at this point, the electric field due to this positive charge is away from the point along this direction. Similarly, you may assume same elemental portion ds at here also. For this one, ds bar is directed along this direction. This is ds bar direction. And E bar at this point P directed radially outward. This is the direction of E bar. Hence, at a given point, electric field intensity and area vector both are parallel to each other. The flux through this curved surface, cylindrical part, how you write? AB, CD for entire this curved surface is equal to closed integral E bar dot ds bar, which is equal to closed integral E ds. What is angle between these two? 0 degrees. Means cos 0. Here cos 0 value is 1. Hence, flux through ABCD curved surface not equal to 0. This is the point. Now we are going to find flux through this cylindrical portion of the Gaussian cylinder. For that, we need area of cross section of this part. What is the length of the Gaussian cylinder? L. Radius is small r. Then the surface area of the curve part is 2 pi r circumference into length L. 2 pi r L is the surface area of this curved cylindrical part, where L is the length of the cylinder. Now, we apply Gauss law. Flux through the Gaussian surface we are going to find. Here, actually 3 surfaces are there. AB is one surface, CD is the second surface. These 2 surfaces are flat surfaces. For these 2 surfaces, flux becomes 0. Only through the curved surface ABCD, flux exists. That flux now we are going to calculate. Flux through the Gaussian surface is only flux through the curved cylindrical part of the surface. For remaining 2 parts, flux becomes 0, which is equal to E into area. Electric field intensity E into area is 2 pi r into L. Already we discussed it. This flux is equal to Q by epsilon naught according to Gauss law. The curved surface encloses a charge Q equal to, here lambda is given. What is lambda? Linear charge density. Then Q is equal to lambda into L. From Gauss law, phi is equal to closed integral E bar dot ds bar, which is equal to Q by epsilon naught. Closed integral E bar dot ds bar is E into 2 pi RL is equal to Q. What is Q? Charge enclosed in the Gaussian surface. That is linear charge density into length of the cylinder. Length of the cylinder is L, then lambda into L is the charge which is enclosed in the Gaussian surface, Gaussian cylinder. So instead of Q, lambda L by epsilon naught. Here L cancelled. Then E is equal to lambda by, bring this 2 pi r to this side, 2 pi epsilon naught r. This is the electric field intensity at a distance small r from a linearly charged wire. Hence, final formula is E equal to lambda by 2 pi epsilon naught r. Vectorially, E at any point is given by, already I explained that if the wire is positively charged uniformly, then lambda is positive. For lambda positive, at a given point, electric field is directed outward. If the wire is negatively charged, hence lambda is negative, then electric field at a given point directed radially inward. Means it can be positive or negative. The direction of electric field vector will be a function of whether the linear charge density, means lambda, is positive or negative. Already I explained here. If lambda is less than 0, that means lambda is negative, implies the wire is charged negatively. Then the direction of electric field is radially inward, means towards the wire. If lambda is greater than 0, that is the wire is positively charged, the direction of electric field is radially outward. Further, the assumption that the wire is infinitely long is crucial. Without this assumption, we can't take E to be normal to the curved part of the Gaussian cylindrical surface. Now, MCQ. The electric field intensity at a point due to line charge distribution at a distance r is directly proportional to. Options are 1 by r, r square, 1 by r square. Electric field intensity due to linearly charged wire, E is equal to, just now we derived formula, that is lambda by 2 pi epsilon naught r. From this expression, the electric field intensity is inversely proportional to distance of the point, that is r. E is inversely proportional to r. But according to problem, how it is directly proportional to? E is directly proportional to 1 by r. Hence, option A is correct. Next question. A long wire carries a charge of 2 into 10 power minus 8 coulomb per meter. Find the electric field at a distance 0.2 meter from it. The given options are 1800 volt per meter, 1850 volt per meter, 2000 volt per meter, 1715 volt per meter. Solution. Here 2 into 10 power minus 8 coulomb per meter. It is the linear charge density of the wire, lambda, is equal to 2 into 10 power minus 8 coulomb per meter. Now, distance of the point r is equal to 0.2 meter. By substituting these two in E equal to lambda by 2 pi epsilon naught r, lambda value is 2 into 10 power minus 8 coulomb per meter, r is 0.2 meter. By substituting here, we get. Here 1 by 4 pi epsilon naught is very familiar to us, that is 9 into 10 power 9. To use this value, E is equal to, I multiply and divide this equation with 2. Then here it becomes 4 pi epsilon naught. Already 2 pi epsilon naught is there. Now I multiply divided with 2. 2 lambda by 2 into 2 pi epsilon naught becomes 4 pi epsilon naught into r. 1 by 4 pi epsilon naught is 9 into 10 power 9 into 2 into lambda. 2 into 10 power minus 8 by r, distance 0.2. Substitute here. In further simplification, we get E as 1800 volt per meter. Means option A is correct. Next problem. A thin-walled copper pipe 3 meter long and 2 centimeter in diameter carries a net charge of 5.8 microcoulomb distributed uniformly. The intensity of electric field 8 centimeter from the pipe axis is. The options are 4.3 into 10 power 3 Newton per coulomb, 4.3 into 10 power 4 Newton per coulomb, 4.3 into 10 power 5 Newton per coulomb, 4.3 into 10 power 6 Newton per coulomb. To calculate this, the formula is E equal to lambda by 2 pi epsilon naught x. Why? Because throughout the length of the copper pipe, 5.8 microcoulomb charge is distributed. From that copper pipe, at a distance of 8 centimeter, diameter is 2 centimeter. Now, at a distance of 8 centimeter means it is the outside of the pipe. At that point, we are going to find the electric field intensity. What formula we are going to use? E equal to lambda by 2 pi epsilon naught x, where lambda is linear charge density, which is charge by length. Charge is 5.8 microcoulomb. 5.8 micro means 10 power minus 6 coulomb by length of the wire, that is 3 meter by 3. In further simplification, the value of lambda is 1.933 into 10 power minus 6. And x, at what distance we are going to find the electric field intensity? 8 centimeter. Centimeter converts into meter. By multiplying 8 with 10 power minus 2. So this is the x value. This x and lambda substitute in the formula E equal to lambda by 2 pi epsilon naught x. Then equal to lambda by 2 pi epsilon naught x, and lambda is Q by L, which is this value. All the values substituted in this equation. E equal to 1 by 4 pi epsilon naught. For adjustment, the value is 9 into 10 power 9 into this value. In further simplification, we get 4.3 into 10 power 5 Newton per coulomb. Option 3 is correct.